All right, guys, welcome back. We are now on topic 5. Topic 5 is called Moving Beyond Slope Intercept. And here today, we are just going to do the student activity sheet 1, which is the overview. Okay, the overview, again, guys, the overview of each section just kind of gives us an idea of what this whole topic is going to be about. Okay, so we all remember Terrence. How could we forget Terrence and his mad skateboarding skills? Well, because Terrence is so good at skateboarding, he is going to teach his friend Teresa how to skateboard also. So Terrence has this own special way of how he teaches Teresa how to do it. And so what he's going to do is he's just going to pull her by a rope on in a straight line. So let's just take a look at what happens here. Okay. With this, when Terrence went ahead and pulled Teresa, they were able to make up this chart of what happened when Teresa moved. So with this, we showed that at 0 seconds, they were 0.7 feet away. So I'm going to kind of just put a check there. And 1 second had gone by, she was 1.1 feet away. And then we've got 2 seconds and 1.5. Guys, these aren't perfect, but just, try to get them as close as possible. 3 seconds is 1.9. 4 seconds is 2.3. 5 seconds is 2.7. 6 seconds is 3.1, 7 seconds is 3.5, 8 seconds is 3.9, and 9 seconds is 4.3, and 10 seconds is going to be at 4.7. Okay, so we'll check that. It looks like it liked my points. So let's go ahead and keep going here. So again, this is Teresa, and Terrence is going to teach her how to skateboard. So I want you guys to look at this. They want us to take Teresa and decide where to start her and see if we can create a graph to match this. So I'm going to do a couple things here. I'm just going to take her all the way back to the beginning, right? We all think that we have to start on 0. But if I do the graph here, aside from my total inability to follow the rise and the run, okay, what do we notice? The first thing I notice is I didn't start in the right spot. I thought we were starting at the beginning. So I started down here at 0, but they show me starting up here. So what that means, guys, is that I've got to actually start Teresa a little bit off. It looks like we're just about to the halfway point there. No, let me reset that again. Maybe get closer to the halfway point. That's close enough. Okay, so you can see, guys, she's not starting at 0. Okay, now when I look at this, it looks like it takes her 3 seconds to travel 2 feet. Okay, 3 seconds to almost 2 feet. So 3 seconds is going to get her to this mark. So let's go ahead and do that. I think I did a pretty good job this time around. I'm a little bit off, but then I get on. Okay, so let's look at our first question. Okay, how did we decide where Teresa should start the skateboarding at? Okay, well, when we looked at this, guys, we decided that when I put Teresa at 0, I didn't match that. I knew she had to come a little bit off. Okay, so with that, how I decided was that because my graph didn't start at 0, that means that we had to start her off of the motion detector as well. What did I also know about this graph is that it went constant. It was a constant graph. It stayed the same throughout the whole thing. It was steady and it was slow. And by slow, guys, I mean it was slow. It took her 3 seconds to travel 2 feet. I don't know if you've been on a skateboard, but you don't do anything slow on a skateboard. Even when you fall, it is very quickly and not usually with any grace. Okay, so let's go on here now. So again, guys, what we have here is the table, but there's some things that I want to take note of. Okay, so this graph that we have over here, it contains all of those data points. I know because we made them. To make this line, we had to drag Teresa at a very steady, constant rate. Okay. And then that constant rate told us the difference between the time and her distance in feet from the detector. This constant representation represented the slope. Okay, that's a new keyword for us. I'm sure several of you guys have heard that before. So I want to take this down. A keyword for us here. Let me get this light on because my lights went off. Okay, a keyword for us here. Slope. Okay. And again, we're going to learn about this more on the next pages, but let's go ahead and get this down. Slope is simply the measurement or just the measure of the steepness of a line. But here's the key thing here, guys. Something that I want you guys to understand. Okay? Make another like regular star here. Remember that fancy rate of change we're learning about? Slope and rate of change are the same. Slope equals rate of change. Okay, here's our two new things so far. Slope is the measure of the steepness of the line, and it is the same exact thing as rate of change. So if you know how to find rate of change, guess what? You already know how to find the slope. Okay, so what we're going to do is we're going to put a little bit more formality on this. So let's do some things here. Okay, they want us to calculate the rate of change. So remember, I just said that's the same as slope. Okay, they want us to calculate the rate of change in these tables by looking at the y values and the x values. Okay, so a lot of times something we're going to learn this time around is that we're going to start to see this little triangle. Okay, we call that delta. And all you guys need to know is that when you see triangle, all that means is change in. Okay, it's the words change in, or what we can call the difference. All right, so let's take a look at how we may use that. Okay, so with this problem, I have the same table here that they have. Okay, they want us to find the change in each of these seconds and each of these points in feet. Well, guys, seconds are our x values. Distance in feet are our y values. So we're going to find the change in x and the change in y. We already know how to do this. We just did this all last unit. We found from 0.7 to 1.1, it increases by 0.4. For those of you that are like, decimals, how in the world am I ever going to do this? Guys, plug into your calculator. 1.1 minus 0.7, and it will give you that number. So if we, guys, all of these would have a change of 0.4. All of these have a change of 1. Okay, but now what they want you guys to see, again, remember when we took our rate of change, okay, all we did, guys, was we created a fraction, the change in y value over the change in x values. This number right here goes on top, this number goes on the bottom. So on this particular problem, we would type in 0.4 feet over 1 second. And all that does is that reduces to a 0.4 of a foot per second. Sorry, per second. Okay. So let's go on here. We're still on question 2. So here, they just want us to see back to table. This 0.4 feet per second, all it does is that little value right here in blue, all the blues are that 0.4 feet, and it goes over 1 second in red every single time. Okay, let's go on. Okay, some more things that we want to talk about this section. So we're going to flip to question 3 here. Okay, question 3. We're going to introduce some new terms in this section right here. Okay, what we have is the y value of a point at which a graph crosses the y-axis. Well, all that is, guys, is what we call the y-intercept. Okay, so where a graph crosses the y-axis. So as an example, if I have a graph right here, and say I've got my line here in pink, something like that. This point right here, where it crosses the y-axis, that is what we call our y-intercept. Okay, that is our y-intercept. So at this particular graph here, okay, where it crosses the y-intercept was at 0.7. How do I know it was at 0.7? Because that's when 0 seconds was. Okay, if you also want to take note, this is always going to be in the format of x comma y. My y-intercept is at the point 0 comma a number. Okay, when x is 0, what is your y value? Something else, you guys may remember this. Okay, we have slope-intercept form. Okay, hopefully you guys remember that. If you don't, we may have to have a conversation. But you guys have been doing slope-intercept form for a long time. That's y equals mx plus b, where m stood for our slope and b is our y-intercept. Our b is this number that goes right here. Okay. So let's go on to question 4. It's taking a while for my screen to load here. Okay, so here we have gas. Alex is driving home from school. His gas tank is reading empty. How many of you guys have parents like that? I always say there's 2 types of parents, or 2, sorry, not parents, but 2 types of people in this world. People who get to like a quarter of a tank and they're like, oh my gosh, I need to get gas. That's me, guys. I do not like to get close to that empty. Have I done it? Yeah. But then we have people in this world that are like, I've been on E for 2 days. We got some fumes left still. I can't do it. I don't know how people do it. One time I got to like, it's literally said like 0 miles till empty, and my heart just raced the entire time. I'm sure I was fine, but I don't like to do it. I wonder if Mr. Case or Miss Latimer, what kind of person do you think Mr. Sears Patowski is? Do you think he's a quarter tank guy, or is he a let it go to E type guy? All questions. Maybe you should ask your teachers about that. Anyway, so we got Alex, okay? So Alex notices his fuel tank says empty. So he's going by a gas station. He's going to get some gas. Alex knows that his car has 12, it's a 12-gallon tank, okay? So to make it totally full, he has 12 gallons. But as he's pumping gas, it goes off and it says that he hasn't even put 11 gallons in his tank. So he tries to add more gas, but then he spills gas everywhere, guys. His hands, his shoes, the bottom of his pants. Oh my gosh, now he has to live with that smell. Okay, what in the world happened? He has a 12-gallon fuel tank. He didn't even put in 11 gallons. How was he full? Okay, so let's think about that. Okay, and so I don't know if you guys are aware of this, but we have these fuel tanks, okay? Most fuel tanks, how this looks, guys, is that we've got our tank, and here's the little sensor. This little plug right here is what says if the fuel tank is empty or full. So right here, it's on the bottom. So our gauge reads empty. However, we have this little section over here that's called our reserve. This is where like that extra gallon is held. You know, like, so when our car reads E 0 miles till empty, you got another gallon to get you where you're going. Now, don't go home and say, Mrs. Stanton says that we could still drive for another one, you know, use one more gallon, which some cars that's like 18 miles, some cars it's 30, you know, it all depends. But don't go home telling your parents I said that. Okay, remember, I'm a quarter tank type of person. So anyways, Alex's fuel tank is a total of 10 inches high right here. Okay, a total of 10 inches high. And it varies with the amount of gasoline that's in that box. Okay, so I want you guys to think from this picture, what happened? And again, I have this happen all the time. I know I have a 16-gallon tank, but I don't put 16 gallons of gas in it every time. Even though Alex filled almost 11 out of the 12 gallons, he still had some left in his tank. That's it. That's the explanation. But let's talk about what this actually looks like. Let me take this back. For some reason, Agile Minds is not wanting to work with my other screen today. So the reading on our fuel's car gauge is correlated with the height of the float inside the tank. So let's take a look at this little, I don't know where my animation is. So as the little floaty box goes up, so does our number of gallons in the tank. And as it gets fuller, and there we go, till it's all the way full, okay? When the height reaches 10 inches, it says that Alex's gauge is full. Okay, so what I want to do on this, guys, let's look here. What is the y-intercept? Okay, what is our y-intercept on this problem? I'd say that it looks like maybe 1.5. Remember, guys, y-intercept is where it crosses the y-axis. Well, here's my y-axis right here. Okay, and if we look over here on our graph, okay, my y-axis, this is where it crosses. It looks to be about 1.5. So I'm going to say that the y-intercept is 1.5 gallons. Well, what does that mean? 1.5 gallons is the amount of gallons in the tank. It means that there was still 1.5 gallons in the tank before he started pumping gas. Okay, so now they want to know for part B, what is the slope? Well, again, we can look on the paper or you can look over here on the screen. It looks to go about up 1 and over 1. You can maybe see it better here. I don't know what kind of drawing I did there. But we go from 1.5 to 2.5 in 1 inch. Okay, so I'm going to call that about 1. I'm going to say about 1. Now, I do think it gets off a little bit because if you notice all the way up here, we actually end on a corner. So it's kind of hard to say, but I'm going to call it about 1 gallon per inch. Okay, almost a full gallon per inch. Okay, something else I could have done. Okay, something else I could have done, guys. I could have said, all right, well, I've got a point right here at 1.5, and I've got a point up here all the way at 12. So how do I get from 1.5 to 12? Okay, well, that's a change of 10.5 gallons. So that's where I got that 10.5 gallons. Okay, so how did I get from 1.5 up to 12? That's 10.5. And how many inches was that? From 0 to 10. So that's where I got the 10. And if we divide that out, it's about 1.05 gallons per inch. Okay. So with that, I'm going to have you guys go back and look at your reinforced questions with your teacher and make sure you ask them if you have any questions. Bye.